Natasha Christian from Group 1, and today I will be presenting the objective and abstract for experiment 4 vapor compression refrigeration. So, what is COP? The coefficient of performance is a performance rating that tells us how effective a heat pump or air conditioner is at transferring heat versus the amount of electrical power it consumes. Essentially, heat pumps and air conditioners move heat from a low temperature area and pump this heat uphill to a high temperature area and against the laws of thermodynamics, which says that naturally heat flows from something that is hot to something that is cold. This uphill movement of heat from a low temperature area into a high temperature area thus requires work, and the COP says how effectively a heat pump or air conditioner performs this work by telling us the amount of power required by the machine to move a certain quantity of heat at a certain temperature from a low temperature area to a high temperature area. The objective of our experiment this week is to determine the coefficient of performance for vapor compression cooling system. That is all from me. I'll pass it on to my next groupmate.
Hi, I'm Lakshmi. Will now present the theory and related application of this experiment. The basis of refrigeration system is a thermodynamic cycle working between two different temperature sources. This cooling system receives heat from a low temperature space and transfer heat to a high temperature space. This process requires work to be supplied to the system as shown in figure 2. Since energy cannot be destroyed, the heat taken in at a low temperature must be dissipated to its surrounding. The second law of thermodynamics states that heat will not pass from a cold region to a warm one without spending any energy or work. Therefore, a refrigerator requires energy input for its operation. Schematic of a vapor compression refrigeration cycle is shown in figure 2. This cycle has following components. Firstly, a compressor which compresses the vapor working fluid and providing required mechanical energy W to its system. The second one, the condenser that absorbs heat at a constant pressure from the working medium and transfer it to the high temperature source. An expansion valve that expands the liquid working medium during a constant enthalpy process. An evaporator facilitates the evaporation of a working medium while it absorbs heat from the low temperature reservoir. The next slide shows the schematic diagram of the refrigeration cycle. That's all from me. Thank you. I'll pass to the next presenter.
Assalamualaikum warahmatullahi wabarakatuh. My name is Ahmad Nidarif and I will continue for the methodology part. The following components are identified: evaporator, condenser, compressors, expansion valves, watt meter, water flows in and out, and the flow of fluid R14B as depicted in figure 3. For each position, the thermometer is observed. The vent valve is not blown out. This is figure 3. Next, operations are launched and readings are recorded. The valve is opened as illustrated in figure 4. Figure 4 is as follows. Next, the water pipe is open. 19 gram per second is set as the water flow rate to the evaporator, and maximum water flow rate to the condenser is also set. Main switch is switched on. Then the cooling system is allowed to stabilize 10 minutes for 10 minutes, and parameters as listed in table 1 is recorded. The experiment is then repeated by changing the flow rate of water to condenser in between 0 to 20 gram per second. The experiment needs to be repeated 4 times. Operation termination. When the experiment is done, the device is made sure to have been closed in accordance to these procedures. First, main switch is switched off. Then, water supply pipes is turned off after 1 minute, and then valves are closed to shutdown position as depicted in Figure 5 after 1 minute. Figure 5 is as follows. Thank you. I pass on to the next presenter.
Hi, Assalamualaikum and good day everyone. My name is Aina Alia binti Abdullah and I will proceed the presentation with the result and discussion of the experiment. First thing first, we need to complete the table of data by calculating the rate of heat transfer of the evaporator and the condenser for the 5 test run and discuss the results. For rate of heat transfer in evaporator, or also known as QL, we will use the formula of Q equals to M delta H. The flow rate of evaporator for this experiment is constant at 19 gram per second or same as 0.019 kilogram per second. The enthalpy can be obtained by interpolating the data obtained from the steam tables on T1 and T2 of every test. So here is the result obtained from the calculation, which is QL is 46.2345 for test 1, 46.2072 for test 2, 46.1754 for test 3, 46.1233 for test 4, and 46.09502 for test 5. Next, by using the same formula, which is Q equals to M delta H, we will calculate the rate of heat transfer of the condenser by using different flow rates for each test. Thus, from this, we could get that QH for test 1 to 5 is equals to negative 43.6596, negative 38.666678, negative 28.9502, negative 19.2668, and negative 9.0612 respectively. After that, from the QL and QH obtained, we will determine the coefficient of performance, COP, by using the equation absolute QL over W net, which also same as absolute QL over QH minus QL. Then we will get the COP for test 1 to test 5 equals to 0.5143, 0.5444, 0.6146, 0.7054, and 0.8276 respectively. Next, we move on to the next discussion where we need to explain the effects of changing flow rate of T1 to T5 to compressor power. From the graph, we can see that the highest compressor power recorded at the condenser flow rate is at 16 gram per second and the lowest is at 4 gram per second. So from this graph, we could conclude that the condenser power will increase as the condenser flow rate increase.
Hi and Assalamualaikum. My name is Muhammad Saifuddin Khan bin Nazaruddin. So finally we are come to the last part of this video, which is conclusion. So in conclusion, the coefficient of performance is directly proportional to the rate of heat transfer in evaporator. It can be concluded that the condenser flow rate is directly proportional to the compression power. In addition, as the condenser flow rate increases, the work input also increasing. Beside that, it also can be summarized that the condenser flow rate is inversely proportional to the temperature change. And finally, this is the reference that we use in this experiment. So I think that's all from us. Thank you.